Okay, so let's start. Welcome to this course on kernel methods. Although it's called kernel methods, we'll spend a lot of time talking about binary classification and different techniques for binary classification. Um, so again, the prerequisites for this course are Introduction to Statistical Learning Theory and Concentration Inequalities. For the initial part, it will have helped if you've taken convex optimization, because we did a little bit of linear classification in that particular course. But I won't really assume any background in convex optimization. We will use some ideas, for example, gradient descent and algorithms for solving some of these optimization problems. But as much as possible, I will try to avoid any overlap. So just like in the previous courses, there'll be two exams, midterm exam sometime during the week of 8th November and a final exam sometime in the week of 25th November. We'll decide the dates maybe by next week or so. There'll be two homework assignments that will be given, but you don't have to submit those assignments. And yeah, in case you would like to discuss something, you're always feel free to send me an email and set up an appointment. We'll finalize these class timings, slot P in A221. The references, I'll keep updating these, but mostly we'll follow the first two books mentioned in this in these, essentially the same as what was followed for the Introduction to Statistical Learning Theory course. Okay, yeah, and I'll update class notes as well as recordings as in the previous courses. Any questions regarding administrative stuff? Okay, so let's get down to it then. So in the first part of this course, we'll talk about linear classifiers, and essentially kernel methods can be viewed as approaches of embedding. The basic idea in kernel methods is to construct an embedding from your given space, from the input space, to a higher dimensional space. So it's kind of the opposite of what is done in dimensionality reduction. The goal is not to go down to a lower dimensional space in order to save computational or space complexity, but rather to map it into a higher dimensional feature space so that somehow it helps you construct algorithms more efficiently. Right? We'll make more of this precise as we go along, and we'll view this from the lens of binary classification. All right. So let's spend some time talking about binary classification itself. Again, it's throughout we will assume the following. So we'll assume that we're doing binary classification in RD. So the input space is going to be RD, and for convenience, I'll assume that the label set is 1 minus 1. I'll sometimes go back and forth between 0 and 1 or plus 1 and minus 1, depending on how things go. Okay. So first we'll explore this specific hypothesis class. Let's use the terminology that we've seen in the previous course. So we'll look at the following hypothesis class, which is the set of all functions h of x, which can be expressed as sine of A transpose x minus b, where A is a vector in Rd and b is an arbitrary real number. right? So this is nothing but this plus 1 if A transpose X minus B is greater than or equal to 0, or A transpose X is greater than or equal to B, and it's equal to minus 1 if A transpose X is strictly less than B. All right. So first, it's a binary classification problem. What is the VC dimension of this class? Right. So it depends on what dimension you are living in. So we're assuming a d-dimensional space. I'm sorry, if so we're allowing all possible A. So right, if you're looking at R2, then the VC dimension would be equal to 3, but in general it is going to be d plus 1. Right. The VC dimension of H is d plus 1, which means that this class is in fact pack learnable, right? And agnostically pack learnable, which is fine, but the problem is how do you do ERM? You can't really solve for ERM because it is computationally complex. So the whole point is to come up with efficient algorithms in order to effectively pack learn this particular hypothesis class. So first is how do we actually perform ERM? Can this be performed efficiently? But also there could be multiple ERMs, right? So even based on the simple examples that we saw in the previous course, the ERM is not necessarily unique. So is there a way of efficiently finding one ERM? And even if there are multiple ERMs, how do we choose among those? Well, if you're dealing with just pack learnability, where the concept class is equal to the hypothesis class, for a given training set, there could be multiple hypotheses which give you zero empirical risk. Right? So even in the case of maybe learning axis aligned rectangles, there are two different ways. One is you could define one ERM was to choose the smallest bounding box for all of those labeled 0, or you could take the largest bounding box outside which you have all of those which are labeled 1. Both of them are valid ERMs, and really you can't really say which one you should choose over the other. Correct. There could be multiple empirical risk minimizers. So it of course, in principle, this doesn't make a difference in terms of pack learnability, but maybe it will help us to design a more efficient algorithm. And there could be other reasons for choosing one ERM over the other. For example, sometimes what we want is stability, in the sense that even if the inputs are slightly perturbed a little bit, the ERM doesn't change. So that's a desirable property in many problems. right? Okay, but first let's explore the geometry of this particular hypothesis class. Right? Let's start with some of the basics. Let's look at set of all x such that A transpose x equal to 0. Right? What does this correspond to? It's some hyperplane passing through the origin, and it's also a subspace. Right? What is the dimension of this particular subspace? X is in Rd, right? So just to make clear, so vector A is in Rd. So what is the dimension? D minus 1, as long as A is a non-zero vector. And we'll assume that A is a non-zero vector. Okay. So this defines a D minus 1 dimensional space. I'm sorry? If A is a zero vector, then what does this set correspond to? A transpose X equal to 0. 0 transpose anything is equal to 0. So what can you say about the set of all X for which A transpose X is equal to 0? It's all of Rd. Alright, so it's a D-dimensional space. Fine, we'll assume that A is non-zero. Okay, so let's first try to answer the following question. Suppose I give you an arbitrary vector x in Rd. Right, so this is some vector x. I can decompose it along the hyperplane and perpendicular to the hyperplane. Right. So what would be the direction that is orthogonal to this particular hyperplane? So effectively these are two directions. So what can you say about this particular direction? It's is it parallel to A or is it anti-parallel? Okay, so let's first look at this. So this vector over here, right? I'm talking about the pink line. So what can you say about the vector in this particular direction? It is orthogonal to every vector in this particular set. Correct? So let me call this set S. All right. So this vector should be orthogonal to every vector in S. Now can you guess what should be the direction of? Should be in the direction of A. That's fine. That's fine. Oh, okay, okay. That's fine. So effectively it's either in the direction of A or in the direction of minus A. Okay.
Then we can push the direction of this.
So if x is such that if okay, maybe I should have used slightly better notation. Let's call this vector y instead of x. So if we know that A transpose y is greater than or equal to 0, then that's a different story. But right now I'm assuming that it's an arbitrary one. Right. So in principle, y could have a component along A or along minus A. Doesn't matter. Okay. So this y can be written as some alpha times the vector A plus beta times some other vector y prime, where this y prime lies strictly within S. Right? And this beta y prime is effectively just the projection of y onto this space. What is the, now this is a subspace. So what is the projection matrix onto this particular subspace? Okay, or in other words, how do you find alpha and beta? Alpha, beta, and y prime. You know that the vector y is equal to alpha times A plus beta times y prime. The set, it's a subspace of dimension d minus 1, right? Everything belongs to R power d. Okay? Okay, equate what to 0?
This is just take a dot product with respect to A.
You take the inner product of this with respect to A. Okay, great. The left hand side, why will the left hand side be 0? So y prime is in S, right? You have to be a little careful. So this y prime belongs to S, right? Based on this picture over here. So you're right, that's one approach. So A transpose y is going to be equal to alpha times A transpose A. Right? So alpha is simply equal to A transpose y divided by A transpose A. Let's make a further assumption that norm A is equal to 1. That will make things a lot more convenient for us. So alpha is just A transpose y. So what is y prime? Whatever beta. This beta was actually unnecessary. I could just call this y prime. Correct. So y prime, which is the projection of y onto the subspace S, is simply equal to y minus A transpose y times A. Right? So what can I say about the projection matrix? So the projection matrix P is going to be the into the subspace S is I minus AA transpose. So this is the projection matrix. Okay, so that's good. All right, so now that we're a little bit comfortable with the geometry of this particular set, effectively every if you look at any one of these classifiers, this essentially corresponds to a hyperplane that is not necessarily passing through the origin. So every hyperplane of the form A transpose X equal to B can be described by the normal vector, which I'll call A, and the shift, which is effectively B. All right. Yes. AB is the set of all X we'll assume that norm A equal to 1 and B is some arbitrary vector, arbitrary number. So this is the normal, and this is what I'll call the shift. Great. So now let's go back to our classification problem. What we're given are a bunch of points, right? Let's look at the problem of Pack learning the concept class H first, right? So this case, we say that S is, maybe again I should have chosen a different notation. Let me call this S. All right, the samples, the training set the training set S in this case is what I call linearly separable. Right? Because it was generated using the labeling was done using some particular hyperplane as the ground truth. So there exists at least one hyperplane that satisfies all the points that are labeled 1 versus all the points that are labeled -1. Right. I have a bunch of points which are labeled +1 and a bunch of points that are labeled -1. And these vectors are drawn according to some unknown distribution. Given this, the goal is to, now we know that there exists an empirical risk minimizer. So the goal is to find one hyperplane that separates these two. but almost always you'll have multiple solutions. Because I'm assuming that the points that the ground truth corresponds to a concept, right? What does that mean? It means that I'm drawing the vectors x according to some distribution on Rd. But how are the labels being generated? The labels are being generated using a particular hyperplane in the concept class. I'm saying that it's packed learning the concept class, right? It's not agnostic packed learning, which means that the ground truth is in fact one element from the hypothesis class H. Is that okay? Yes. Yeah. So I'm assuming it's the realizable case. Yes.
Is there any set that the ground truth OPXY belongs to the class?
It need not belong to, right? That's why it's agnostic. If you're only restricting to hypothesis, if you're only restricting to concepts from the hypothesis class, then that is packed learning, right? That's the realizability assumption. Correct.
And that I thought the ground truth belong to the what else?
No, the point is if you're dealing with agnostic packed learning, the ground truth could be from the hypothesis class, need not be from the hypothesis class. You have to be able to handle the worst case scenario, right? So you cannot make any assumption. Of course, in agnostic packed learning, it's the most general framework, right? There are specific instances where it can be generated from the hypothesis class, but there's no guarantee that it is going to come from the hypothesis class. It could be anything. It could be any deterministic function, or there could be an arbitrary joint distribution between x and y. Right? So right now we're just dealing with the realizable case. So, sorry, the hypothesis class. What does that mean? So packed learnability is a property of the hypothesis class, right? So it means that if the ground truth belongs to the hypothesis class, then you can learn it with certain guarantees, right? So these are two different frameworks. Right? It depends on what your assumptions are. I don't follow. What kind of a definition are you looking for? I don't quite follow that. But by definition, that's agnostic packed learnability, right? You want to be able to learn, but the ground truth need not belong to the hypothesis class. Then, of course, you can look at the scenario, the non-realizable case, where you have a certain concept class, but the hypothesis class could be different. Right? You can look at the number of different variants depending on what kind of assumptions you have. You could look at scenarios wherein you don't do full agnostic packed learning. That is, you restrict the class of distributions according to which x and y are being drawn, and you have a certain fixed hypothesis class. Instead of looking at all possible joint distributions, you could restrict yourself to a subclass of joint distribution. Right? But again, the more assumptions you make, the worse it is, because you want something that involves the least number of assumptions. All right, so here, I mean, for the same set of points, I can construct multiple solutions, which are all empirical risk minimizers. Which one should I choose? Why?
Because then there's chance of errors.
Good point. So that's one reason that it ensures that the algorithm is stable in some sense. So even if I perturb each of these points by a little bit, each of the input points a little bit, the labels don't change. Now, if I take this particular green colored classifier, if I perturb this point by a little bit, then the label changes from +1 to -1. The same holds for this red classifier. If I perturb this by a little bit, it moves across and that gets labeled as -1. So in an intuitive sense, it helps if we choose the orange classifier because even if I perturb any of the points a little bit, the labels don't really change. So that's one reason. Another reason is that, as we'll see, it helps us formulate this as we can actually solve for this more efficiently. Okay. Exactly as you said, I'm going to try to maximize the minimum distance to any of the training points. All right. So what do I want? I want to construct an ERM. Effectively, what are we given? We're given some training set S, which is set of points x1, y1, x2, y2, xn, yn, and an ERM is one for which is effectively some a comma b such that the sign of A transpose X minus B is equal to Yi for all I. Every ERM has to satisfy this. Another way of looking at this, and that will be particularly helpful, is that Yi, if I look at Yi times A transpose X minus B, this has to be greater than 0 for all. So I'm just saying that this is equivalent to this, right? These are just equivalent ways of looking at it. Effectively, this means that Yi and A transpose X minus B have the same sign. Correct? Okay. So as we discussed, which one now among these ERMs, which one to pick? Let's try to pick the one ERM that maximizes that. Of course, it has to be an ERM, and also maximizes the minimum distance to the hyperplane. All right. So given a point, what is the distance or minimum distance of that particular point to a hyperplane? So given an arbitrary vector x in Rd, A in Rd, B in R, norm of A equal to 1, what is the minimum distance? Is min overall the distance from x to EAB. What is it equal to? Okay, that's the length of the orthogonal project. Okay, orthogonal projection. What will it be? Be a little careful, because in that case it was A transpose Y when we are looking at hyperplanes that were passing through the origin. Right? Now it's no longer passing through the origin, so there'll be a shift. All right, but how much should the shift be? B, so plus B or minus B? Y minus, what do you mean Y minus B? B is a real number. Yeah, so it turns out that it's equal to A transpose Y minus mod of A transpose Y minus B. Let's prove this. So let's look at I'm sorry, this should be A transpose X minus B, because I'm looking at the distance from X to T A comma B. Which one? So I'm minimizing overall vectors in this hyperplane, right? So if you go back to this particular picture, then given this particular vector y, what is the closest point in this particular hyperplane? It would lie somewhere over here, right? What I want to know is what is the distance from between these 2 points, or in other words, in this particular picture, what is the length of the pink colored vector? Any questions?
It will be always random.
Which one?
Between X and the set.
Yes. Why is it? We're dealing with RD and the two norm, right? So
Yes, but we have a over there, right? So like from that notion we are defining D of X and a set. If that we take that as a form of this. Like,
okay, so this is a distance between a point and a set.
yes, can we say we can't compare those things.
It's not really whatever. It's something that is derived from a metric, right? So it's not between pairs of objects of the same kind. So I'm not sure in this case what a triangular inequality would be for this particular case. Okay, so let me define V as the closest vector um, to X in this particular hyperplane, which is going to be X minus A transpose X minus B times the vector A. Right? What is the distance between X and B? It's just mod of A transpose X minus B. Right? Okay, good. Now let's consider any other U that lies in the hyperplane. If I'm able to show that the distance from X to U has to be greater than or equal to this, then I'm done. So let me just write this as, okay, in fact, let me directly use triangular equality. This is less than or equal to norm of, let me do it a little differently. Let me look at X minus U the norm of X minus U the whole square, which I'll write as norm of X minus U, and I'll add and subtract V. Which is X minus V plus U plus V minus U. Well, and let me expand this out. This is just norm of X minus V the whole square plus norm of V minus U square plus 2 times the inner product between X minus V and V minus U. I know that V minus U, norm of V minus U the whole square is non-negative. So this is greater than or equal to norm of X minus V squared plus 2 times the inner product between X minus V transpose V minus U. But what is X minus V equal to? It's A transpose X minus B times A. So it's A transpose X minus B times A transpose V minus U. right? What is A transpose V equal to? A transpose V is equal to B because V lies on the hyperplane. What about A transpose U? That is also equal to B because U also lies in the hyperplane. So what is A transpose V minus U? It's 0. So this is x minus V the whole square plus 0. Right. So no matter which U you pick on the hyperplane, the distance from x to U is always greater than or equal to the distance between x and p. What do you mean the projection vector is unique?
The point
Okay.
the point in which that is projected.
Okay.
That is,
Yes.
and any other
Sure. If I pick any other V, then any other U, then it's strictly greater than. In fact, if U is not equal to V, then this would be strictly greater than 0. So I do have a strict inequality. Right. So this means that the minimum distance between x and the hyperplane is equal to mod of A transpose x minus b. All right. Okay, that's fine. So now let's go back to the problem of designing our hyperplane classifier or linear classifier. The goal is to maximize the minimum distance to the hyperplane. Right. So back to the problem. Find AB, which corresponds to an ERM that maximizes the minimum distance to the hyperplane defined by A and B. Right? This quantity, the minimum distance between the training set and the hyperplane in question or the classifier, this has a special name. It's called the margin. Minimum distance from S to PAP. So effectively, you want an empirical risk minimizer that maximizes the margin. We want arg max overall A and B with the 2 norm of A equal to 1 of the minimum I from 1 to n of I want the distance, so which is mod A transpose xi minus b. And this should hold, I mean, I can't just choose any AB that satisfies this, I want to also be able to, it should also classify things correctly, such that whatever the different ways, let me say yi times A transpose xi minus B is greater than 0 for all.
There can be multiple ERM.
Why? It's not clear yet, right? But hopefully it is going to be unique, right? So we'll reformulate this in two different ways, right, which will hopefully help see what happens to the set of solutions. So first, I have a bunch of conditions. So my end goal is to somehow formulate this as a nice, smooth convex optimization problem. Right? What can I say about this particular problem? It's a constrained optimization problem, but can I say something about the convexity of this particular? Is it a convex optimization problem, the way I formulated it here? I'm sorry? The min, but there's even more fundamental problem. I'm sorry? I don't put the argument of what? There's an arg max here, right? Okay. Whatever, when I say convex optimization problem, it could be minimizing a convex function or maximizing a concave function. Equivalent, okay? That's okay. I mean, this is a function, right? If I treat this as some, because this doesn't depend, this is not independent of the variable that I'm optimizing over, right? We don't know if it's a convex function or not, but there's a direct way of seeing that this is not a convex optimization problem. Okay, why does this not necessarily satisfy a convex? There's an even easier way of seeing it. Objective function is not convex. Yeah, norm A equal to 1. This is not a convex set. Just that. So this is not a convex optimization problem. Right? We'll now try to reformulate this by sort of, again, it won't help us solve this more efficiently, but it will give us a cleaner optimization problem. So I'm sorry, which one? This one. Yeah, correct. I could say that this is effectively part of the constraint. Which one is a convex set?
Like if we just put it as a
No, it doesn't. So it's the same thing, right? The constraint set has to be convex for it to be a convex optimization problem, right? So as long as you have this constraint, it's not a convex optimization problem. If I had norm x less than or equal to 1, then maybe it's a convex optimization. At least that constraint would make it a convex set, right? The question. Okay, great. So then we'll reformulate it in a certain way. We'll write this as I claim that this problem. Let me call this problem 1. Right, which is finding argmax overall a comma b of minimum overall I mod a transpose xi minus b, subject to the constraints that norm a equal to 1 and yi times a transpose xi minus b is greater than 0 for all I. Okay. So first I'll try to get this or get rid of this strictly greater than 0 terms. I claim that this is equivalent to argmax overall a comma b. Again, I do have the constraint that norm of a equal to 1, but now it is minimum overall I from 1 through n of yi times a transpose xi minus b. It's not a convex optimization problem here. I'm not saying that this is a convex optimization problem, but this in some sense simplifies or reduces the number of constraints that I originally had. I'll later again bring back all of those constraints again, but let me call this problem 2. But my first claim is that these two problems are equivalent to each other. Which one becomes negative? Um, you, you're having the concern that effectively in this case I'm only maximizing over positive functions, whereas here this minimum could potentially be negative. Right? Correct. But my claim is that that will not be an issue because because it's not just a minimization problem. I'm also maximizing overall a comma b. So for a given a comma b, you're perfectly right that this quantity could be negative for certain a comma b, but I claim that because I have this argmax, you're also having a maximization outside. This will end up being positive all the time. Question.
What is the minimum value, number of points having negative?
Which? No. This is a function, right? It's a function of x and y. It's minimum over all 1, 2, 3 up to n. Which one? Correct. So yi is either +1 or -1. Right? So again, this is a function. This whole thing is effectively some function of a comma b. Right? You're given a training set. So n pairs of xi, yi. This could be arbitrary, but but one property that you know is that these are linearly separable. That's a fact that I'm going to use. Okay, they are linearly separable, which means that this whole thing has a solution. All right. Mod of a transpose xi minus b is the distance. Exactly. So this, for a given a comma b, this quantity need not be the minimum distance to the hyperplane. You're perfectly right. Right. So for an arbitrary a comma b, this f of a comma, so if yi times a transpose xi minus b, if this is greater than 0 for all I, then this quantity gives me the distance between the training set and the hyperplane defined by a comma b. But now I don't have these constraints anymore. So in general, this quantity f of a comma b for an arbitrary a comma b is not going to be the distance between the hyperplane and the training set. You're perfectly correct. So I can't really interpret this exactly as as maximizing the margin, because this does not give me the margin for every a comma b. For certain a comma b, this actually gives me the margin, but for some a comma b, it does not give me the margin. Yeah, the point is that the solution to this problem is equal to the solution to this particular problem. That is all that I'm trying to claim. All right. So in fact, let me define a set. Let me call this G. Let's call it the good set, which is the set of all A, B are such that norm of A equal to 1 and yi times A transpose xi minus B is greater than 0 for all I. All right. So this is basically the set of all. This is the set of all ERMs. Right. So these are all those classifiers which correctly classify your given training set. Okay. Okay. So now for any a comma b in G, which is for any ERM, what is min of overall I in N of basically this objective function that I had above? What does this evaluate to? So it gives you the margin, right? It's equal to minimum overall I in N of mod A transpose xi minus B, right? Because I know that this quantity is greater than 0, so it's going to be 8 mod of A transpose xi minus B. Okay. Correct.
Problem to be over those points, but when you are taking a function, we consider only those points.
Ultimately, that is what.
In that case, when we running time, problem 2 may run even more time.
You can't really say anything yet, because here again the running time is determined both by the objective function as well as the constraint. In this case, I don't have any additional constraints apart from the fact that norm A is equal to 1. The search space of problem 2 is, I agree, it could be more than that of problem. But effectively, the relevant vectors are those which are the constraints, which satisfy the constraints of problem. All right. Okay, great. So my point is that the solution to problem 2 is always going to lie in G. Let's look at problem 2. I'm taking the maximum. And my claim is that the a comma b that achieves this is in fact going to lie in G. Why? It's R max. There's at least one solution which achieves a positive value of max min. So so therefore, instead of maximizing over all a comma b, I might as well just maximize over all a comma b that achieves a positive value of f of a comma. Right? And if I'm only maximizing over G, what do I get? I just get back problem 1. So problems 1 and 2 are equivalent. Any questions? Okay. Now I'll introduce another problem. Problem 3, which I'll call hard SVM, or SVM standing for support vector machine. Which is the following. So now the problem is, let me call this. So the hard SVM problem is the following. So you find, set A naught B naught, A0 B0 equals arg min overall A comma B of the 2 norm of A the whole squared. No constraint that the 2 norm has to be equal to 1. But now it is subject to the constraint that yi times AI transpose xi minus b is greater than or equal to 0 for all I. I'm sorry, a transpose xi. And then finally you output A0 by norm A0 and B0 divided by norm A0. Okay, so firstly, what kind of a problem is this? I'm sorry?
Change the constraint to minus.
Minus of that less than or equal to 0, okay. Why do I have to change it to minus? Okay, I mean, that's in standard form.
Yeah.
That's a standard form, right? But nevertheless, this is a convex optimization problem. It's in fact a quadratic optimization problem. I have a quadratic objective function and I have a bunch of linear constraints, right? So this is great because I know how to solve this efficiently. And I mean, this A0, B0 is not exactly my solution. I'm finally going to normalize A0, B0. All right.
The one 0, 0.
Won't, oh, correct. I'm sorry. I made a mistake. It should be greater than or equal to 1. Thanks for pointing it out. I'm going to set this to be greater than or equal to 1, not greater than or equal to 0. Now 0, 0 will not be a solution. Okay. All right. My claim is that problem 2 and problem 1 is the same as hardest wheel. Okay, so to see why that is the case, okay, let's consider, so let A star and B star be a solution of problem 2. Okay, and let the minimum value of the objective function for problem 2, let me just call this gamma star. So this is equal to max overall AB with norm A equal to 1 of min overall I of yi times AI transpose, sorry, A transpose xi minus b. Okay. So what does this mean? It means that yi times A transpose xi minus bi is greater than or equal to gamma star for all I. And just because this is gamma star, I'm sorry, this should be this for this solution A star B star. So there is an A star B star that achieves this particular gamma star. So for all I, yi times A star transpose xi minus B star should be greater than or equal to gamma star. Just 1 second. It is going to be the distances. Since gamma star is equal to min overall I in n yi times a star, oops, a star transpose xi minus b star, right?
The max should
I'm sorry?
take gamma star of that
Correct.
max of
Yes.
that quantity, then we would have greater than
Oh, so I'm saying that this maximum is achieved by an a star b star, right? So you agree that gamma star is equal to this? I'm sorry? Okay, so I'm saying that a star b star is a solution for this, right? Okay, so there is an a star and b star which achieves max of min of this. Okay, so what would be, and I'm saying that gamma star is the value of this particular objective function. It's the maximum of all minimum distances. That is gamma star, correct? So what would be min overall I of yi of a star transpose xi minus b star? That would be equal to gamma star, because I'm claiming here that this gamma star can be achieved, that this is not just a supremum, it's in fact a maximum. It can be achieved, right? So you agree that gamma star is equal to this particular quantity, which means that since this is a minimum overall I, for every I yi times this is greater than or equal to gamma star. I can't say that for every a comma b satisfying these constraints this is greater than or equal to gamma star. Okay. Okay, good. Now, if this is true, what can I say about yi times a star by gamma star transpose xi minus b star by gamma star? What is this? This is greater than or equal to 1 for all I. Right? Again, I've made another subtle assumption over here that gamma star is strictly positive. Okay. But what does this mean? It means that a star by gamma star and b star by gamma star, they satisfy the constraints of the hard SVM problem. Right? So, yeah, a star by gamma star. I'm not normalizing it. So in this case, a star has norm exactly equal to 1. I'm in some sense unnormalizing. So a star by gamma star does not have norm equal to 1. Gamma star satisfies constraints of hard SVM. Right? Yeah.
for what particular constraint gamma star would be
For what particular constraint?
what can be like A and B
Huh.
for which gamma star? Like is there can I take a particular set of points?
Okay.
Which gamma star comes?
In fact, if you're given an arbitrary training set, you can always choose something with gamma star strictly greater than 0.
equal to 0.
Not equal to 0, strictly greater than 0.
Yes.
Yes. You can think about it a little bit, why it's always possible.
Like we can choose the gamma star strictly greater than 0, but will there be a possibility for gamma star equal to?
What do you mean you can choose a gamma? So gamma star is well defined, right? It is the maximizer. Okay. Yeah. Sure. Okay, we're almost done. So this satisfies the constraints of the hard SVM problem, right? So what can I say about the norm of A0 star, or the norm of A star divided by gamma star? Gamma star square, this is greater than or equal to norm of A0 square, right? Because A0 is the solution to the hard SVM problem, and it is the one that minimizes the L2 norm among all points that satisfy these constraints. But this is equal to 1 by gamma star square. Correct? Now, similarly, if I look at yi times A0 transpose xi minus b0, if I look at the normalized vectors, right, this is, we know that this numerator part is greater than or equal to 1 because A0 satisfies the constraint. It's a solution to the hard SVM problem. So this is greater than or equal to 1 by norm A0. Correct? But just from what we had over here, norm A0 is less than or equal to 1 over gamma star, and therefore this quantity is greater than or equal to gamma star. All right. So the minimum over all I, this is true for all I. So the minimum over all I of yi times A0 transpose by norm A0 xi minus b0 by norm A0, this is greater than or equal to gamma star. Can it be strictly greater than gamma star? Why? Okay, so what is the definition of gamma star? Gamma star is by definition the max of this particular function among all vectors of unit norm. A0 by norm A0 has unit norm. So therefore this has to be equal. Right? But what is A0? A0 is a solution to the hard SVM problem. And the maximum of this is basically problem 2. So problems 2 and the hard SVM problem are equivalent. A0 is a solution for, or I should say A0 by norm A0 and B0 by norm B A0 is a solution for problem 2. So I can solve the hard SVM problem, which is a convex optimization problem. and get a solution to problem 2. But we saw that problem 2 is effectively the same as problem 1, which is maximizing the margin. So the max margin can be solved by solving the hard SVM problem, which is a nice convex optimization problem that we can solve. Okay, so let's stop here. Any questions?